Hi everyone, today we're going to talk about topic 7.12, the common ion effect. One way we can think of solvents whenever we're trying to dissolve something is like a bag or like a suitcase, right? If you're trying to travel somewhere, you want to put a bunch of stuff in your suitcase, you can only put so much stuff in that suitcase. Think of the suitcase as the solvent and all your clothes and everything as the stuff you want to put in it. A solution is exactly the same. When you have too much solute or too much salt dissolved, then at that point, it just wants to fall out. It won't go into solution anymore because there's no more room for the water to help contain all the salt in there through the IMFs, right? It's the ion-dipole interactions that help keep the salt in the water. But if you don't have enough water in order for all that salt, then it won't dissolve anymore. And so what happens if I try to dissolve calcium fluoride, CaF2, in a solution that already has enough F- ions to precipitate compared to that of pure water? Well, that's what we're going to talk about in this kind of topic here. So the common ion effect is quite a simple rule. It basically says that if one of the ions in solution in equilibrium, and so essentially what we're thinking here is KSP, right, dissolving something in solution in order to dissolve it, or putting something in a solution to dissolve it, and it's already dissolved in solution. So basically I have my little container here. I have some water, and I already have, say, CaF2 dissolved in there, right? So I have some Ca2 plus, and I have some F minus already dissolved in this water. What it's saying is it's already dissolved. The solubility of the salt will decrease. In other words, if I already have salt in the solution, the solubility goes down. And so in this example, if I have either Ca2 plus or F minus in that solution, then the CaF2 is less soluble compared to if I had pure water. And you can kind of see this right here in this chart. Here we have molar solubility of CaF2. This is in molar, right, our normal solution for concentration, or for solubility. And down here, we have the concentration of sodium fluoride, right? And so here what we're doing is we're adding Na plus and F minus. So here we're adding Ca2 plus and F minus. We see that the Ca and the Na are not the same, but we have a common ion here, and that's the F. And so if we look at this graph right over here, we can see as I add more and more and more sodium fluoride, NaF, the solubility of CaF2 goes down. And that's because I already have F minus in solution. And so, of course, we can think about this in terms of Le Chatelier's principle. Since we already have NaF in solution, we already have Na plus and F minus in solution. This means that there's an increase in F minus ions. Because there's an increase in F minus ions, this is going to want to shift to the left. Or in other words, we'll have more CaF2, and so it does not dissolve. You can kind of expect this, right? It's similar to what we saw with reactions. If I increase the right side, if I put more stuff into the right side of my reaction, into the products, it's going to want to go back to the reactants. Same idea here. If I try and dissolve CaF2 in a solution that already has Ca2 plus or F minus, I'm not going to want to dissolve it. And so you have a lower equilibrium concentration of both ions, both Ca2 plus and F minus, which means that less CaF2 can actually dissolve. Now let's actually do a practice problem on this. We're essentially going to be doing a rice table, but because we already have some products in there, things work out a little bit differently. So of course, for our rice table, our reaction here is CaF2 in equilibrium with Ca2 plus and 2 F minus. And what we're told here is we want to dissolve CaF2, but now we know the starting concentration of CaNO3, which is just Ca2 plus NO3 minus, two of those, is 0.01. And so if we look at a reaction here, what this is saying is I'm going to write this up here, already have Ca2 plus. And so in previous examples, right, our products are always 0, but in this case, we're told specifically that our products are not 0 at the start of our reaction. So let's draw a size table. Of course, CaF2, this is a solid, and so we ignore all the terms in our Rice table. For Ca2+, we're told we have 0.01 molar Ca2+, so at the start we have 0.010 molar, and we have no F-. For change, this is the same as before, right? It's a product, and so we have plus some amount x. And then for F-, we have two of those, so it's plus 2x. And then for the change here, now this is 0.010 molar, because that's what we start with, plus x. We're going to gain some amount of x. And then for F-, it's just 2x. And then, of course, we plug it in to our expression here for KSP. KSP is equal to 0.010 molar, molar plus x in the parenthesis, times 2x, and that will be squared. Of course, KSP is 3.9 times 10 to the negative 11th. And what you'll notice here immediately is that this problem will work out a little bit different compared to other ones. If we actually go ahead and factor this out a little bit, we'll see we have 0.010 plus x times 4x squared. That should equal 3.9 times 10 to the minus 11th. And then if we distribute this, we should have 0.010, 4, my bad. We should have 0.040 x squared plus 4x cubed equals 3.9 times 10 to the minus 11th. And then if we get everything to each side, it's 0 equals 4x cubed plus 0.04 x squared minus 3.9 times 10 to the minus 11th. And of course, this is not very trivial to answer on its own. You'll have to use a calculator. And of course, you do have a calculator on the exam, but we can use the assumption we talked about before, which is that KSP is very small. Right, our number here is 3.9 times 10 to the negative 11th. And so just like we did in previous problems, we can ignore this term because x is going to add pretty much nothing to 0.01 because KSP is so small, we can assume that x is significantly smaller than 0.01. So now, given this assumption, I'll rewrite KSP. This is going to be equal to just this portion, 0.010 molar, times 2x squared. And so now, KSP equals 0.010 times 4x cubed. All of this will equal 3.9 times 10 to the minus 11th, and all we're doing here is solving for x, and we find that x is equal to 3.1 times 10 to the negative 5th molar. And of course, this is significantly smaller than 0.01, so that assumption holds true, right? In this case, x is less than 5% of 0.01. And so with most of these problems, we can use that assumption where we ignore the term plus x. And so, of course, the answer here, the molar solubility, is going to be this number right there. So you can see these problems proceed pretty similar to our KSP problems as before, just with the added complication that now you have a starting concentration there, and so you need to consider this particular assumption that we were making before. So I'm going to write up here, consider the assumption. We'll have a little bit more practice in class, but for now, that's all. Thanks, guys.